Okay, so derivatives of vector valued functions are pretty straightforward. Okay, so if our vector r of t is a vector valued function, then the derivative of r with respect to t is going to be r prime of t, which is the limit as h approaches 0 of r of t plus h minus r of t all over h, which is just following directly from the idea of a derivative in R2. Essentially, if you think about what's going on here, you have a particle that's following some sort of path, and let's say this is the time t that I'm taking the derivative at. If I were to cut that path and let that particle just move along inertia, the resulting vector r prime of t is that vector. So it's going to send us off in the direction that inertia would take us from that point. Okay, so this is kind of an important idea in physics, right? All right, so let's kind of move with this a little bit here. Okay, so since this resulting vector is the inertial vector at time t, we might want to be able to describe that vector as a unit vector. So we're going to call that the unit tangent vector. And a unit tangent vector is going to be represented as capital T at time t. And this is just the derivative vector at time t over its own magnitude. Okay, so that's what's making it a unit vector. So if I take that, divide it by its own magnitude, so we're going to call this the unit tangent vector of r at time t. Awesome, so it's good that we know that this thing exists. It gets me in the inertial direction and it has a magnitude of 1. Okay, so the limit definition of a vector, or of a derivative, is never entirely useful because it makes it very difficult to calculate. So we're going to state a quick theorem here. The theorem says that if r of t, that's ugly, that's really ugly. If r of t is f of t, g of t, h of t at time t, then and f, g, and h are all differentiable. Aha, differentiability has to be shown. If these limits all exist, then the derivative vector is just the derivative of the components. F prime of t, g prime of t, h prime of t. Woohoo. Okay, so that means that this thing does exactly what I want it to do. You can compute the derivative by computing the derivative of the components. I'm not going to prove this. The concept of the proof is just simply that since limits are computed component-wise and derivatives are limits, it seems to follow that derivatives should also be computed component-wise, and in fact that is going to bear out. Okay, so nothing too odd there. All the typical rules for derivatives just follow through because they follow through over the components. So three big ideas here. One, the derivative is still a limit as we define it. Two, you have this idea of the direction of inertia and that unit tangent vector. And three, to do this, you just actually compute the three component derivatives, and then you have the derivative and the direction of inertial motion. So, pretty simple.